This is the first 3 lessons on the gyromagnetic compass. The gyromagnetic compass is an instrument which evolved out of the need to overcome the limitations of both the direct reading magnetic compass and the directional gyro indicator. We'll start by reminding ourselves of these limitations, and then go on to see how the design of the gyromagnetic compass removes or eliminates them. The direct reading compass has 3 major limitations. These are: firstly, turning and acceleration errors. The compass cannot be read accurately during a turn. Secondly, the magnetic sensing element. That is, the group of magnets on the vertical card is contained within the instruments and has to be situated close to the pilot so that the card can be seen. Unfortunately, the cockpit area is close to sources of deviation, such as electric lights, electric motors, and ferrous metal. Finally, it is a stand-alone system. The instrument is self-contained. It is not possible to take magnetic heading from it as an electrical or mechanical input into other equipment, such as those which display bearings from ground radio beacons, the autopilot, and the flight data recorder. The directional gyro indicator attempts to solve some of these problems by use of an air-driven or an electromechanical gyro. Turning and acceleration errors are eliminated, and outputs can be taken to other equipment, for instance, to display radio bearings. However, there is no magnetic input to the heading. There is no correction except by the pilot manually synchronizing to the direct reading compass at regular intervals. What is required is a system which combines the best of both. The short-term rigidity of the gyro overcomes turning and acceleration errors. This needs to be combined with the longer-term monitoring of the Earth's magnetic field, so that if the gyro starts to drift, a servo system slaves it back to alignment with a magnetic input. Such a system is called a gyromagnetic compass. The gyromagnetic compass is known by several names. It can be referred to as the gyromagnetic compass, remote indicating compass, slaved gyro compass, magnetic heading reference system. They all mean the same thing. A more modern version, which often includes other functions, such as the display of VHF omni-range, usually shortened to VOR, is known as the horizontal situation indicator, or HSI. The system comprises the following elements: a magnetic detector unit. This is also often known as a flux valve or a flux gate. Note that it is usually mounted on a wingtip or on top of the fin, and is therefore well removed from most of the sources of deviation. A compass indicator dial. This is what most people refer to as the compass. A precession amplifier. This may also be known as a slaving amplifier. A precession motor. This may also be known as a slaving or synchronizing motor. And a horizontal gyro, similar in principle to the one used in the DGI. In simple systems, the horizontal gyro is directly connected to the compass card of the indicator dial through 2 cogs, which change the rotary motion through 90 degrees. This is called a bevel gear, and it works like this. We are assuming our gyro is connected to the compass indicator dial by a bevel gear in the description which follows. The purpose of the detector unit, or flux valve, is to sense the Earth's magnetic field and reproduce it within the compass indicator. We will explain how this is done later. At this stage, we'll just say that magnetic heading has been detected electronically and passed to the indicator in the form of alternating current, or AC. We'll also assume that the compass has already been initially synchronized, in order to make the gyro drive shaft output to be the same as the flux valve. Again, we'll cover how this is done later. In the compass indicator box, the flux valve output is compared with the position of the gyro drive shaft. This is the shaft which positions the compass card indicator, that is, the heading shown to the pilot. If the two are aligned, no further action takes place. The compass card is reading the right heading. We'll assume a steady heading, which gives a steady input from the flux valve. From this point, any difference between the flux valve field and the gyro alignment would only arise if the gyro were to drift. If this happens, the drive shaft will not be in alignment with the flux valve field, and an AC error signal is generated and passed to the precession amplifier, where it is amplified, phase detected, and rectified to direct current, or DC. The DC signal drives the precession motor, which turns the gyro. This gyro output is fed via the direct drive shaft to the HSI, for comparison with the flux valve signal. If the two are aligned, the compass is synchronized, and no further action takes place. If not, the error connection continues until the compass is synchronized. We now have a system in which if the gyro drifts away from the steady flux valve heading, it is brought back again by the precession amplifier and motor. We have explained the normal operation in terms of the gyro, which has a tendency to drift, being slave to the magnetic detector unit. However, there is also a smoothing of the signal the other way, because the magnetic flux valve signal itself is subject to short-term fluctuations, and the effect of these is reduced by the gyro. Let's see how. The magnetic field detected by the flux valve is generally stable over periods of tens of minutes or of hours, but it can fluctuate for short periods of up to 2 or 3 minutes, particularly during accelerations and turns. Suppose that, for some reason, the flux valve signal has temporarily introduced a small error. This will be compared with the gyro signal, and the error will be detected. The system has no way of telling whether the error is in the flux valve or the gyro, and so the error signal will start to drive the gyro to follow the flux valve. However, the precession motor is designed to take the error out slowly, correcting the gyro at a rate of only 3 degrees a minute, or thereabouts. The gyro will therefore respond slowly to this short-term error. The error may well disappear before the gyro has turned significantly. If not, as soon as the flux valve signal is correct again, the gyro will follow it back to the correct value. So, because of the choice of precession rate of the motor, any small short-term flux valve errors are damped out by the gyro's slow response. We therefore have a system which combines the best of both sources, the short-term rigidity of the gyro and the longer-term monitoring of the Earth's magnetic field. Now consider what happens in a turn. We will assume initially that the gyro does not drift during the turn, which may well be the case, because even during a full 360-degree orbit at the standard rate 1, the turn will only take 2 minutes. The aircraft turns, but the gyro, having rigidity, does not. This gives relative rotation between the horizontal gyro and the instrument case, and so operation of the bevel gear causes the direct drive shaft to rotate, changing the heading indication on the compass card. However, at the same time, the heading sensed by the flux valve, which is being passed to the drive shaft for comparison, is changing at the same rate. Therefore, no error signal is generated, and the compass should remain synchronized during the turn. If, in fact, there is some gyro drift during the turn, on completion of the turn there will be a small error signal. This will be taken out, as described in the previous scene. The use of a slow precession rate gives us a problem at startup. On initial switch-on, the alignment that the gyro takes up is random, and is unlikely to be in synchronization with the Earth's magnetic field. Therefore, an error signal is detected. The problem is that the precession motor's normal correction rate is designed to be only 3 degrees per minute, in order to smooth out short-term fluctuations. And if the gyro happened to be 90 degrees out, it would take 30 minutes to synchronize, which is obviously unacceptable. The solution is to have a rapid synchronization facility. This can either be a mechanical clutch operated by the pilot, as in the DGI, or, in later compasses, a high-gain mode for the precession amplifier, similar in principle to rapid erection in the electric artificial horizon. This is operated by a two-position switch, spring-loaded to the normal position, which has to be held against the spring for rapid alignment. Operation of this switch increases the precession motor's correction rate, so that synchronization takes only a few seconds. More modern compasses are even more automatic. If a large error is detected, fast precession takes place at typically 60 degrees per minute until the error is 0. Then the system automatically reverts to the slow, smooth precession rate of typically 3 degrees a minute. We therefore have to modify our original block schematic to include the rapid synchronization facility. We still have 2 more lessons to come on the gyromagnetic compass, one on the flux valve and the other on the remaining components. But let's summarize what we've covered so far. The direct reading compass suffers from turning and acceleration errors. Is situated close to the pilot, but also to sources of deviation, such as electric lights, electric motors and ferrous metal, and is a self-contained instrument. It is not possible to take magnetic heading from it as an electrical or mechanical input into other instruments. In the directional gyro indicator, turning and acceleration errors are eliminated, and outputs can be taken to other equipment. But there is no magnetic monitoring. We therefore have a system which combines the best of both sources: the short-term rigidity of the gyro and the longer-term monitoring of the Earth's magnetic field. We looked at all the basic components. This system has several advantages over the direct reading compass and DGI. Firstly, the flux valve is usually mounted on a wingtip or on top of the fin, and is therefore well removed from most of the sources of deviation. On initial switch-on, the gyro is brought into alignment with the signal detected at the flux valve. From then on, the outputs of the gyro and the flux valve are compared. If there is any error, the gyro is precessed into alignment with the flux valve by the precession amplifier and precession motor. This overcomes the normal gyro drift. The flux valve on its own would still suffer from turning and acceleration errors, but sending the signal via the gyro gives stability and rigidity, because the precession motor applies corrections to the drive shaft at the rate of approximately only 3 degrees per minute. In a turn, both the flux valve and the gyro shaft turn at the same rate, so there should be no significant error at the end of the turn. If any error is generated in the turn, it will be small, and is precessed out in the normal way after completion of the turn. Finally, we modified our block diagram to include the rapid synchronization facility. This concludes the lesson. We will look at flux valve theory in the next session.